Hidden field equations. Hidden fields equations HFE, also known as HFE trapdoor function, is a public key cryptosystem which was introduced at Eurocrypt in 1996 and proposed by Jacques Patarin following the idea of the Matsumoto and Imai system. It is based on polynomials of a finite fields letter 1d5 3d key of different size to disguise the relationship between the private key and public key. HFE is in fact a family which consists of basic HFE and combinatorial versions of HFE. The HFE family of cryptosystems is based on the hardness of the problem of finding solutions to a system of multivariate quadratic equations, the so-called MQ problem, since it uses private affine transformations to hide the extension field and the private polynomials. Hidden field equations also have been used to construct digital signature schemes, e.g., Quartz and Sflash. Mathematical background. One of the central notions to understand how hidden field equations work is to see that for two extension fields letter 1d5 3dq and letter 1d5 3dq m over the same base field letter 1d5 3dq, one can interpret the system of meters multivariate polynomials in n variables over letter 1d5 3dq as a function letter 1d5 3dq and right are letter 1d5 3dq m by using a suitable basis of letter 1d5 3dq and over letter 1d5 3dq. In almost all applications the polynomials are quadratic, that is, they have degree 2. We start with the simplest kind of polynomials, namely monomials, and show how they lead to quadratic systems of equations. Consider a finite field letter 1d5 3dq where q is a power of 2 and an extension field Kelvin. Let 0 HQn such that h equals q theta plus 1 for some theta and GCDH qn minus 1 equals 1. The condition GCDH qn minus 1 equals 1 is equivalent to requiring that the map u right arrow UH on Kelvin is 1 to 1 and its inverse is the map u right arrow UH where h is the multiplicative inverse of h mod qn minus 1. Take a random element u letter 1d5 3dqn. Define w letter 1d5 3qn by w equals UH equals uq theta 1. Let beta n to be a basis of Kelvin as in letter 1d5 3dq vector space. We represent u with respect to the basis as u equals u, un, and w equals w, wn. Let k equals hk be the matrix of the linear transformation u right arrow uqk with respect to the basis beta n, that is such that $beta iqk equals \sum j equals 1n hk \beta j \hk \n map fq for 1 less or equal to I, k less or equal to then. Additionally, write all products of basis elements in terms of the basis i.e. $beta I \beta j equals \sum l equals 1n mal \beta l mal in math fq for each 1 less or equal to I, j less or equal to n. The system of n equations which is explicit in the w, I and quadratic in the u, j can be obtained by expanding 1 and equating to 0 the coefficients of the beta I. Choose to seek affine transformation south and t, that is 2 invertible n times n matrices ms equals sh and mt equals th with entries in letter 1d5 3dq and 2 vectors vs and vt of length n over letter 1d5 3dq and define x and y via u equals sx equals msx plus vsw equals tie equals mtie plus vt2 by using the affine relations in 2 to replace the u. J, W, I with X, K, Y, L. The system of n equations is linear in the Y, L and of degree 2 in the X. A. Applying linear algebra it will give n explicit equations, 1 for each Y, L as polynomials of degree 2 in the X. A. Multivariate cryptosystem. The basic idea of the HFE family of using this as a multivariate cryptosystem is to build the secret key starting from a polynomial p in one unknown x over some finite field letter 1d5 3dq and normally value q equals 2 is used. This polynomial can be easily inverted over letter 1d5 3dqn, that is, it is feasible to find any solutions to the equation px equals y when such solution exists. The secret transformation, either decryption and slash or signature, is based on this inversion. As explained above, P can be identified with a system of n equations Pn using a fixed basis. To build a cryptosystem, the polynomial Pn must be transformed so that the public information hides the original structure and prevents inversion. This is done by viewing the finite fields letter 1 d5 3 dqn as a vector space over letter 1 d5 3 dqn by choosing two linear affine transformations south and t. The triplet S, P, T constitute the private key. The private polynomial P is defined over letter 1 d5 3 dqn. The public key is Pn. Below is the diagram for MQ trapdoor S, P, T in HFE. $text input x \text equals x1 x and /overset /text secret s / x /overset /text secret p / y /overset /text secret t / text output y $. HFE polynomial. The private polynomial P with degree d over letter 1 d5 3 dqn is an element of letter 1 d5 3 dqn. If the terms of polynomial P have at most quadratic terms over letter 1 d5 3 dq, then it will keep the public polynomial small. The case that P consists of monomials of the form xqsi plus qti, that is with two powers of q in the exponent, is the basic version of HFE, that is P is chosen as px equals summation c Roman 9 qsi plus qti. The degree d of the polynomial is also known as security parameter, and the bigger its value the better for security, since the resulting set of quadratic equations resembles a randomly chosen set of quadratic equations. On the other side, large d slows down the deciphering. Since P is a polynomial of degree at most d, the inverse of P, denoted by P-1, can be computed in d2 ln d union 2 letter 1 d5 3 dq operations. Encryption and decryption. The public key is given by the m multivariate polynomials Pn over letter 1 d5 3 dq. It is thus necessary to transfer the message m from letter 1 d5 3 dq and right arrow letter 1 d5 3 dqn in order to encrypt it. That is, we assume that m is a vector x and letter 1 d5 3 dqn. To encrypt message m, we evaluate each pi at xn. The ciphertext is p1x, xn, p2x, xn, pnx, xn letter 1 d5 3 dqn. To understand decryption, let us express encryption in terms of STP. Note that these are not available to the sender. While evaluating the PI at the message, we first apply S, resulting in X. At this point, X is transferred from letter 1 d5 3 dqn right arrow letter 1 d5 3 dqn, so we can apply the private polynomial P, which is over letter 1 d5 3 dqn, and this result is denoted by y letter 1 d5 3 dqn. Once again, y is transferred to the vector y1, yn, and the transformation t is applied, and the final output y letter 1 d5 3 dqn is produced from yn letter 1 d5 3 dqn. To decrypt y, the above steps are done in reverse order. This is possible if the private key SPT is known. The crucial step in the deciphering is not the inversion of south and t, but rather the computations of the solution of px equals y. Since P is not necessary at bijection, one may find more than one solution to this inversion. There exist at most d different solutions x equals x1, xd letter 1 d5 3 dq, and since P is a polynomial of degree d, the redundancy denoted as r is added at the first step to the message m in order to select the right m from a set of solutions x. The diagram below shows the basic HFE for encryption. $m /overset plus r /x /overset /text secret s /x /overset /text secret p /y /overset /text secret t /y $. HFE variations. Hidden field equations has four basic variations, namely plus, v, and f, and it is possible to combine them in various ways. The basic principle is the following. 1. The plus sign consists of linearity mixing of the public equations with some random equations. 2. The sign is due to Adi-Shamir and intends to remove the redundancy r of the public equations. 3. The f sign consists of fixing some f input variables of the public key. 4. The V sign is defined as a construction and sometimes quite complex such that the inverse of the function can be found only if some V of the variables called vinegar variables are fixed. This idea is due to Jacques Patarin. The operations above preserve to some extent the trapdoor solvability of the function. HFE and HFEV are very useful in signature schemes as they prevent from slowing down the signature generation and also enhance the overall security of HFE, whereas for encryption both HFE and HFEV will lead to a rather slow decryption process, so neither too many equations can be removed HFE nor too many variables should be added HFEV. Both HFE and HFEV were used to obtain Quartz. For encryption, the situation is better with HFE+, since the decryption process takes the same amount of time. However, the public key has more equations than variables. HFE attacks. There are two famous attacks on HFE. Recover the private key Shamir kidneys. The key point of this attack is to recover the private key as sparse univariate polynomials over the extension field letter 1d5 3d keyren. The attack only works for basic HFE and fails for all its variations. Fast Grabner basis forger. The idea of forger's attacks is to use fast algorithm to compute a Grabner basis of the system of polynomial equations. Forger broke the HFE challenge 1 in 96 hours in 2002, and in 2003 Forger and Jew worked together on the security of HFE.